In this video, we will talk about resistance and about Ohm's law. But before we can really talk about it in detail, let's define our vocabulary. So there are several new uh, words that we will have to learn about. There is the word resistance, right, which physics is denoted by this symbol capital R. It has units of ohms, right? So one can write it out as OHM, or one, and sometimes we also write it as use the Greek symbol uppercase omega to denote units for resistance. Of course, this can all be related to SI units through omega or ohms being equal to volts by ampere. Okay, and you should probably try and work out how you can reduce volts by ampere into something that is an SI unit form, which means kg, meters, seconds, and amps, and so on and so forth. So what is resistance? One can call it it's a characteristic property of a conductor, and is a measure of how much a conductor resists electric flow. Okay, so just like the electron tries to move through a wire, there can be some forces that oppose that motion of the electron, and so it's a property of the material and also of the design of the material, that is its dimensions and so on and so forth, that determine what the value of its resistance is. So in electric circuits, we implement resistances through what we call resistors. And in class, you will deal with resistors that look like this. And what is the real difference? Why do we use things like this? Well, when we want to use very specific values of resistance, then we use components like this, and these are all color coded. And these color coded these color codes actually, you can read what these color codes are, and we will do that in class, where we will read what the color codes are and identify how many ohms of resistance this corresponds to. Should note that every electric component, including wires and bulbs, all of them have some amount of resistance. What these resistors do is they let us implement very specific values of resistance. Suppose I wanted exactly about 100 ohms of resistance. If I wanted exactly 100 ohms of resistance, then I would use one of these resistors. On the other hand, a wire or a bulb doesn't have very specific values of resistance. All right, the next thing we need to understand is resistivity. So these are just, I'm introducing vocabulary here. So this is resistivity. Its symbol is rho, okay? And units are ohm multiplied by meter or ohm meter. And this really is the intrinsic property of a material that determines how strongly it resists electric current. And how is it different from resistance, right? You should ask, how is this different? Well, here resistivity only depends on the material. Resistance depends not only on the material, but it also depends on the dimensions of the material, that is how thick a wire is or how long a wire is. And so we will talk about that briefly as well. The link between resistivity and resistance. And already from the units itself, you can see that there must be some kind of link. And the reason that there's a meter there means that, again, we're talking about the dimensions of the material. Alternate definitions, instead of using, so very often, especially in biology, we don't use resistance and resistivity as measures of electrical conductivity. We use the words conductance and conductivity. So they're they're alternate. You don't you could use either resistance and conductance, or you could use either resistivity, or you could use conductivity. So but so that means they're all related to each other. So the conductance, for example, is given by the symbol G. It has units of inverse of omega, and sometimes it's also written as MHO, or Siemens with the S. Um, and it's the inverse of resistance, so G is really equal to 1 by R. And conductivity, similarly, we denote it usually with the symbol sigma. It has units of omega inverse, M inverse, so or Siemens per meter also sometimes. Um, and so it's the inverse of resistivity, and so sigma is equal to 1 by, or the inverse of resistivity. And so these are just things that you need to be familiar with, that if you're given conductance, you can easily calculate resistance. If you're given conductivity, you could easily calculate resistivity. And finally, the thing we will touch upon is Ohm's law, which relates current and voltage. So if V is the voltage and I is the current, then the voltage is proportional to the current, and we can write it as V is equal to I times R, where R is the resistance. Okay, so with that, let's first start motivating resistance. And so let's go back to our picture in previous video. We had spoken about why electrons move through wires and what happens when you connect a battery through a wire. And so to remind you, there's this battery. There's this battery over here, right? So this is a symbol for the battery. And that's probably what battery looks like. And so remember that the larger side had a plus, or had a positive, was the positive side, and the smaller side had the negative side, right? So what a battery is trying to do is it you could think of a battery as a capacitor, except it somehow has an endless supply of of uh, um, electrons. So so it's not exactly a capacitor. It is different from a capacitor, but you could think of it like that. And what do I mean by that? You can say that, all right, so the negative side has lots of electrons. Okay, and what does it naturally tend to do? And the positive side is deficient in electrons. There are more of the ions left behind, and so it has some kind of. So if you were to connect a a voltmeter across and measure the voltage, you would see that the battery would have some potential difference between the positive and negative terminals, right? So this is just like a capacitor. If there's a uneven charge, if the plates are charged, then you would see some kind of potential difference across the plates. Now, the battery tries to maintain this potential difference, right? So when you read readings on a battery, it says 1.5 volts, or 9 volts, or 12 volts in a car battery. So what the purpose of the battery is that it's always trying to maintain that amount of voltage. It tries very hard, and usually if the circuits are fine, you will not it is successfully able to maintain a 1.5 volt or a 9 volt voltage across it, and it does this through chemical reactions, and maybe we will talk more about this later. But so that's what a battery is doing. And so when it does that, if there's this voltage across it, it the you would normally think that the best way for the electrons to travel would be to just jump to this side, but it cannot do that, right? It's physically incapable of doing that, and that's how the battery has been set up, right? So the only way that these electrons can start moving around is to move around this way through the circuit, right? Um, to move around in the circuit this way, so and try to get to the positive side somehow. So so coming back to the picture, um, if I thought about one, say, cylindrical component of a resistor, and it had some length, it is of length L, right? And so if I think of if all the electrons for some reason are on this side initially, right? Eventually all the electrons will flow through, but I'm just looking at the initial picture. So there's some excess of electrons here, so that will create a potential difference like we showed last time. So there's a potential difference where the electrons pull this potential down on this side more, and so the electric energy goes up here, and if there's an electron somewhere over here, it's going to be pushed away, and then eventually more electrons come from here and they all get pushed, and so then this just completes a circuit, and electrons keep going round and round this circuit. Okay, so so that was the picture we came up with last time. Okay, so if I know, for example, if I can use the big square, and I know that this is the electron over here, I want to find out how quickly does the electron move, right? So suppose it's sitting over here, and then because of all of these electrons, it experiences some, or because of the battery, really, it experiences some electric field. Then what is going to happen to this electron, right? Well, it experiences a net force that is going to be Q times E, right? The net force on the electron is just the charge of the electron multiplied by the electric field generated by the battery or the other distribution of charges in the wire. So if that is the case, then what happens to how does this move? How will the electron move? Well, we know that mass times acceleration, the net force is equal to mass times acceleration from Newton's law. And what that would mean is that if this was a uniform electric field or a constant electric field, if this was constant, then the acceleration would be QE over m, and so that means the electron would keep traveling at a very fast, would accelerate at this rate. Okay, so let's talk about why this is a problem. Okay, what contradictions do we come up with? Well, if this was the case, the electron would then keep accelerating, and so if I had a really long wire, the electron would just keep accelerating very, very fast. Sorry, would speed up and would start moving very, very fast, and eventually you would see that you might even you might go to very high speeds, and which will not make any sense. And the problem really there is that in experiment, this is not what we see. In experiment, we see that the electron moves with a constant velocity. Okay, so electrons move with constant velocity, so this cannot be correct. Okay, so we have to just scrap this. This cannot be correct. Now, I won't go into the details of this, but I'll just try to motivate it a little bit. So if you go back to this picture of the electron cloud, so this is a metal. Here you have at all these different sites the nucleus or the charged ion of each metal, and here you have this electron cloud. Well, this electron cloud is more like a gas of electrons. Okay. Now, one caveat is that I have to really understand electric conductivity in resistors, you'll have to think about quantum mechanics, but we won't talk about that. I'm going to give you a simplified model of how electrons move. And at some point, this model also breaks down, so that's just a caveat. For our class, we don't care about quantum effects, so we won't bother about them at all. And it's enough to just think of this as a gas of electrons, or some classical gas of electrons. And what we've seen in class is that if I have, say, for example, a microbead moving around in some solution that we've seen like under the microscope, then it moves with a constant velocity, right? It moves with some constant speed. And the reason why it's moving with some constant speed is because it's actually traveling at terminal velocity, right? And what that means is that there is actually some resistive force acting on these charged beads, and the same thing is happening to the electrons. Okay, so roughly speaking, you can think of this is not an accurate description, but it's an analogous description. You can think of the force that resists the motion of the electron as some kind of viscous force that is slowing the electron down as it's moving through this cloud of gas. So this electron gas cloud. So so I have to actually modify this equation. So this equation is no longer correct, right? So I will have to rewrite that as, I have to add a term that accounts for the resistance to the motion of the electron, and so I'm going to write that down as minus b times v. So this is again motivated by you can think of this as something that looks like a viscosity force, a viscous force, right? Remember that viscous forces, at least for spheres, were proportional to velocity, so we can write something down like this. Okay, so if it's moving at terminal velocity, then at terminal velocity the net force is 0, right? And so I can write QE is equal to BV, right, if I rearrange that equation. Now, what I really want to do is to somehow relate currents, okay, which I've written out here, and I'll remind you in a second what this means, all this means, and voltages, right? So delta V over here. Again, using the big square, the electric field is simply minus dV dx, okay? And in this case, or delta V minus delta V delta x, in this case, the change in x is just the length of the wire. And if I'm going in this direction, then there are various minus signs which all cancel out, and I'll just rewrite this as delta V by L. Okay, so the change in voltage across the wire divided by the length of the wire. Okay, so that's the electric field. Now let's come to this equation for a second. Here V, what was the current defined as? Current was defined as the amount of charge flowing per unit time across some given a unit area of this conductor, of this wire. So Q here represents the charge of the electron, N represents the density of the electrons, V is the same velocity over here, right? The terminal, really the terminal velocity, and A is the area, the cross section area of this wire, right? So this circle over here, that area over there. Okay, so if that's the case, then I can look at this V and rewrite this equation as V is I divided by QNA. And then what I want to do is to substitute this V in here. And if I do that, if I make those two substitutions, then I get, remember, I can make this substitution, so QE. So E, instead of writing E, I write it as delta V by delta L, okay, by L is equal to, so BV, but V I can now write as I divided by QNA, okay. And now if I rearrange everything a bit, so I move this Q down there and I move the L up there and I rearrange everything a bit, then I can relate the voltage or the potential drop or the potential difference to the current, so B Q squared NA times the current. Okay, so now all of this algebraic manipulation is not so important. It's just to show you the important steps of getting of how I can think about relating voltage and current together. Okay, so I end up with something that looks like this. Okay, so the important thing I'm trying to tell you is that we have somehow related the potential difference to the current flowing through the circuit. Okay, and this term in front turns out to be the resistance of the wire, R. Okay, so that's really what Ohm's law is telling us, that the change in potential, and sometimes we don't even write the change in potential because um, although the actual correct expression is change in potential, we usually just abbreviate it as V is equal to I times R, and so that really is what is the content of Ohm's law. And in another video, there will be an explanation of how we use these in circuits and why it's useful. But over here, this is just a motivation of how we relate voltage and current together, and what is the role that resistance plays. Okay, so here you can already see that resistance depends on some kind of intrinsic property of the material. So what's the intrinsic property here? There is this B, the charges of the charge carriers, so with the charge of electrons, the density of those electrons. So all of these are intrinsic properties of the material. But A really is the dimension of the material, right? So A has some dimensions to it, okay? And in fact, resistance and resistivity, so resistance and resistivity are related in the following way. Resistance is R is equal to rho L by A. Okay, and so what that means is that if I have some material, say iron or aluminum or copper, right, then each of these has some intrinsic property of resistivity, rho, right, and that depends on things like how much or how large, say, the viscous force is, how large the viscous force is in that material, and that can depend on the arrangement of the ions and things like that, and um, things like how many charge carriers, what is the density of electrons that are there, and so on and so forth. So those depend on what the material is, and the resistance itself is given by the length of the wire. So the length of the wire and the cross-section area of this wire. Okay, so resistance is related to resistivity through this rho L by A, and this is what I meant by saying that resistivity is just an intrinsic property of the material, whereas resistance is both, that it is both the intrinsic property as well as the dimensions of the wire or the resistor.